Chapter 13, Complex Reaction Mechanisms. Section 13.2, Steady-State Approximation. The simplest sequential reaction mechanism involves two elementary steps. Step 1, from A to I. Step 2, from I to P. I denotes intermediate. There are two different rate constants here. From A to I, it's K sub A. From I to P, the rate constant is denoted by K sub I. Since we have three species involved in the mechanism, we can write out three differential equations. dA over dt is negative Kaa, di over dt is Kaa minus Kii, dP over dt is Kii. If I has a much higher energy than both A and P, it can be very unstable, both thermodynamically and kinetically. The production rate constant of I is then much smaller than that of its consumption. That means Ka is much smaller than Ki. It takes a very long time to form I from A, but then once I is formed, it's converted to P immediately. And in this case, we may assume that I is extremely low throughout the reaction. The change of the concentration of I with time is therefore negligible. Therefore, di over dt is approximately 0. And we know the analytical expression of di over dt. That's Ka minus Ki. Over here, Ka is the production rate of I, Ki is the consumption rate of I. So we have this approximately equals 0. Using this equation, the concentration of I is approximately Ka times the concentration of A over Ki. And because A is always A naught times e to the power of negative Kat, during the reaction mechanism, we have I is approximately Ka over Ki times A naught times e to the power of negative Kat. For the sequential reaction mechanism from A to I and then from I to P, we can make the steady-state approximation for the intermediate I if it's high energy. And then we have I equals Ka over Ki times A naught times e to the power of negative Kat. dP over dt is Ki. This is the exact analytical expression, and we plug in this expression here. Well, dP over dt is approximately Ka, and A is A naught times e to the power of negative Kat. Now we have another differential equation to solve. If the initial concentration of P is 0, we do know P is just A naught minus A minus I, and because I is much smaller than both A and P throughout the reaction, we have this equation, and P is approximately A naught times 1 minus e to the power of negative Kat. We can verify this. We can take dP over dt, and what we will get is going to be A naught multiplied by Ka multiplied by this exponential function, right? So if you take the first derivative of this with respect to time, you get Ka times this exponential function, and then multiply by A0, A naught, it's just this. Now what if the initial concentration of P is non-zero? Well, then P is simply P naught plus A naught times 1 minus this exponential function. When Ka is much smaller than Ki, the production rate of P, dP over dt, equals Ki exactly, is roughly equal to the consumption rate of A, and that's Ka. Well, this is just because once A is converted to I at a very slow rate, I is immediately converted to P. So the rate limiting step of this sequential mechanism is from A to I. Again, Ka is much smaller than Ki, so this reaction is much smaller than this reaction, and this is a sequential mechanism. In a sequential mechanism, the slowest one is the rate limiting step. So the first step is the rate limiting step. And also we know the concentration of I is very low throughout the reaction because it's immediately consumed once produced. In this case, we may assume the steady-state approximation for the intermediate I, which is di over dt is approximately 0. Now let's look at a more complex sequential mechanism. Now we have two intermediates. The reaction proceeds from A to I1, the first intermediate, from I1 to I2, the second intermediate, and then from I2 to P. If I1 and I2 are both high energy species, we can make steady-state approximations for both I1 and I2. Therefore, di1 is over dt is 0, di2 over dt is 0. The exact expression of di1 is Ka minus K1 I1. The exact expression of di2 over dt is Ki K1 I1 minus K2 I2. And it's also roughly 0. And why is that? Well, it's just because I1 is produced in the step from A to I1. The rate is Kaa over here. I1 is consumed in the second step. The rate is K1 I1 right here. I2 is produced in the second step. The rate is K1 I1 right here. It's consumed in the last step. The rate is K2 I2, so minus K2 I2 over here. Now if we can use the steady-state approximations for both I1 and I2, then we have Ka equals K1 I1 equals K2 I2. So we have these equations. And because dA over dt is negative Ka over A, we have A equals A naught times e to the power of negative Kat. So because A is involved only in the first step, it's just simple first order reaction rate law over here. And dP over dt is equal to K2 times I2 in the last step, and this is equal to K1 I1, and this is equal to Ka A, and then we have Ka times A naught times e to the power of negative Kat. If the initial concentration of P is 0, then P is just A naught minus A, and this is just A naught minus A. Alright, because the expression of A is A naught times the exponential function, therefore P is A naught times 1 minus that exponential function. What if the initial concentration of P is non-zero? Then we need to include that P naught here in the expression. That's it. The rate limiting step of this sequential mechanism is this, from A to I1, because the production rate P is limited by this slowest step of the sequential mechanism. So again, this Ka is much smaller than K1, the Ka is much smaller than K2. Let's look at one numerical example problem, 13.2.1. We have a complex sequential mechanism for species from A to I1 to I2 to P. We have the values of the three rate constants. Ka, K1, and K2 are 0.001 per second, 300 per second, 500 per second. Well, you can see this case of A is much smaller than K1. It's also much smaller than K2. So obviously from A to I1 is the rate limiting step. Given the initial concentration of A, we can calculate the concentration of A and P at any other time, for example 200 seconds. We can also estimate the concentrations of I1 and I2. Now let's use this first order reaction rate law. At t equals 200 seconds, A is A naught times this exponential function. This is actually exact. This is just first order integrated rate law. We plug in all the numbers, we get 0.164 molar. I1 and I2 are much smaller than A and P, because I1 and I2 are highly energetic. Once they are produced, they are immediately consumed. Therefore, we can assume P is just 0.2, the total, minus the concentration of A, 0.164 at 200 seconds. we get 0.036 molar. Now if we make the steady state approximation for I1, we have Ka equals Ki, K1, I1. We're plugging all the numbers. Ka, this is Ka, this is K1. This is the concentration of A at 200 seconds. Now we get the concentration of I1, which is 0.000000546 molar, which is indeed much lower than A and P. We can make the steady state approximation for I2 as well, and then we have K2 I2 equals K1 I1. This is a typo. This is supposed to be I2, and then we compute I2. It's also very small. It's about 3 times 10 to the power negative 7 molar. The rate limiting step, again, it's A to I1, only because this Ka is much smaller than K1, Ka is much smaller than K2. Alright, so it takes a long time for A to be converted to I1, but once I1 is produced, it's converted to I2 immediately. Once I2 is produced, it's converted to P immediately. And this is why both I1 and I2 are really low in the reaction.